Welcome to this machine learning case study. Today we're going to be covering the paper titled Mapping Soil Pollution by Using Drone Image Recognition and Machine Learning at an Arsenic-Contaminated Agricultural Field by Jia et al. Arsenic is a very toxic heavy metalloid. It enters the environment through natural sources such as lithogenic processes and anthropogenic sources such as mining and fertilizer manufacturing. Arsenic bioaccumulates in crops and leaches from soil into groundwater, and elevated soil arsenic hinders the achievement of sustainable agriculture. This creates an importance for mapping soil arsenic. It provides policymakers with scientific support when implementing soil protection measures, and it helps choose effective and sustainable remediation strategies. The steps in traditional soil mapping methods include collecting soil samples in a grid pattern and chemically analyzing them to determine arsenic levels, then using geostatistical interpolation methods, or GIMs, such as Kringing interpolation, to predict contaminant concentrations at unsampled points. Traditional soil sampling methods are costly, slow, and not well suited to highly heterogeneous soil environments. The authors propose a novel method to map soil contamination by combining high-resolution aerial imaging, HRAI, with machine learning, ML, algorithms. The study objectives were as follows. Develop reliable approaches to quantify the required features and extract them from the HRAI. Construct models based on different machine learning algorithms and compare their prediction performance. Explore the factors influencing model performance. And illustrate its feasibility by comparing the performance of this method to traditional GIMs. This study contained 3 broad steps. First, detailed soil contamination information and HRAI data was obtained to create the input layer. Then they decomposed the image into pixels and extracted the features of the pixels representing the sample points during the feature extraction layer portion. Then, to create the prediction layer, several machine learning models were trained with the obtained features and evaluated for model performance. The study area was located in southern China. 2 test areas were selected based on a grid located around 2 phosphate factories. Test area 1 is in the orange and near this factory 1. Test area 2 is in the green and is near factory 2. During the input data and feature extraction steps, 1,068 agricultural soil samples were collected and chemically tested to determine arsenic levels. An HRAI image of the study site was obtained, and the image was then matched to the geodetic coordinate system of the sampling points to yield this image. During machine learning model training, the prediction classifiers were trained using the following machine learning classification algorithms: Support Vector Machine, or SVM, Multi-Layer Perceptron, or MLP, Random Forest, or RF, and Extreme Random Forest, or ERF. 50% of the soil sample point data was used for training, and 50% was used for validation. The prediction performance of the different machine learning models was then evaluated. R1 indicates low risk level, R2 indicates medium risk, and R3 indicates high risk. WSA stands for whole study area, TR1 indicates test area 1, and TR2 indicates test area 2. The random forest and extreme random forest models performed best at predicting risk levels, and all models performed best in test area 1. A contribution analysis was then conducted. The extreme random forest model was selected to analyze how important each feature is for making predictions. What the authors determined was that for the whole study area and test area 2, the distance between the data point and the factory was the most important feature for prediction making. And regarding test area 1, the most important feature was the presence of chemical storage. The HRAI-based ERF model was then compared to the traditional geostatistical interpolation method, or GIM. It was found that the ERF outperformed the GRM across all study areas regarding the F1 score and accuracy. The random forest and extreme random forest models performed the best out of all 4 models tested. These models predicted risk better than the traditional interpolation methods. The authors state that the model performance could be improved by identifying and extracting features in more detail or combining HRAI-based predictions with in situ detection methods, such as X-ray fluorescence, to generate more training data at a lower cost. The proposed method has the potential to map soil arsenic to help various relevant decision-making processes. If you would like to learn more, you can find the paper at this full citation. Thank you for watching.